section 6.1 on polygons. And first we're going to look at diagonals. Now a diagonal is a segment that goes from one vertex to a non-adjacent vertex. So if I start up at this top vertex, here is a diagonal, there is another diagonal. I can't draw a diagonal to an adjacent vertex because that's already the side of a polygon. So this is what we're talking about when we refer to diagonals. If I came down to this vertex, I already have this diagonal drawn in, so this would be another new diagonal. There's another one, and there would be our last diagonal. All the diagonals are in there. The reason why these diagonals are significant is because they're going to help us figure out the sum of the interior angles. Now, a polygon with the fewest number of sides would be the triangle. And if I look at a triangle, how many diagonals can I draw from any vertex? Well, I can't draw any, so 0. How many triangles do we have here? 1. I know that the sum of these interior angles then is 180 degrees. So this is our basis for all the other ones. We already knew that a triangle added up to 180 degrees. Let's go on to our next shift, which would be quadrilateral. Quadrilateral is the term that for any kind of polygon that has 4 sides. Specifically, there's squares, rectangles, rhombi, kites, trapezoids, but just any kind of quadrilateral. So I'll make one that isn't specific at all. And the question is, how many diagonals can you draw from one vertex? So from this vertex, have that one diagonal. And by drawing in this diagonal, it created 2 triangles. And this triangle at the top, angles 1, 2, and 3 add up to 180 degrees. And then for this other triangle, we have angles 4, 5, and 6 that add up to 180 degrees. So this 180 plus that 180 gives us a total of 360 degrees. And maybe you're thinking, well, why don't you draw in the other diagonal? As soon as I do that, it creates 4 triangles. And if I look at this one, for instance, one thing I notice is that this angle of the yellow triangle doesn't make up any of the vertices of the original quadrilateral, so I really don't want to deal with this yellow triangle instead. These angles in the triangles all make up the original angles of the quadrilateral. So 1 plus 4 plus 5 plus 6 plus 3 plus 2. Those angles make up the original angles in the quadrilateral. All right, on to our next shape, which is the pentagon. If I my pentagon from any one vertex, I'll pick this one. I can draw 1, 2 diagonals. Yeah, 2 diagonals, which created 3 triangles. 3 times 180 gives us 540 degrees. The next polygon is a hexagon. Hexagon has 6 sides. So at this point, we need to start thinking about patterns that we see. If one of the vertices, there's 1, 2, 3 diagonals, which created 1, 2, 3, 4 triangles. 180 times 4 gives us a total of 720 degrees. You're starting to see this pattern. The next shape we have is the heptagon or septagon. 4 diagonals, making 5 triangles. 5 times 180 would be 900 degrees then. I'll go for one more. This is called the octagon. Octagon has a total of 5 diagonals. That creates a total of 6 triangles, and then 6 times 180 would give you 1080 degrees. And we can keep going and keep going and keep going. Eventually, though, we have this pattern, and we want to use it to get a formula. The one thing I notice is that the number of sides in the polygon leads to the number of diagonals we can get from any vertex. So octagon has 8 sides, we got 5 diagonals. Octagon had 7 sides, we have 4 diagonals. So whatever this is, we subtract 3. So this would be n minus 3 diagonals. To go from this column to the next column, we added 1. If we add 1 onto that, it becomes n minus 2. And then from this column to the last column, the most significant one, we took whatever this number was and multiplied it by 180 degrees for each of those triangles. So we get this formula, n minus 2 times 180 for the sum of the interior angle. Very important formula for us. If you have a convex polygon with n sides, the sum of all the interior angles is going to be n minus 2 times 180, where n is the number of sides. Very important formula for us. All right, so going back to some vocabulary we had from before, we had regular triangles. In general, any regular polygon is going to be both equilateral and equiangular. The equal angular part is the part that we're going to focus on right now. So if we think about how big is each angle in a regular polygon, again, we know they're all the same. So if we do n minus 2 times 180, this gives us the sum of all of those interior angles. That was the formula we just looked at. And since all of those interior angles are the same, if we divide that by n, that will give us a measure of each one. Example, find the measure of each interior angle in a regular hexadecagon. So the hex is 6, the deca is 10. This would be a 16-sided polygon. So first of all, we're going to figure out what is 16 minus 2 times 180. What is the sum of all of those interior angles? So go to your calculator, multiply those, and I got 2,520 degrees for all of them. So if we want to know how big is one, we're going to divide that by 16 to give us a total of 157.5 degrees. So if we have a regular hexadecagon, a regular polygon with 16 sides, each of these interior angles is going to be very big, getting close to 180 degrees, and it just very slowly is going to start bending around. Eventually, we'll have all 16 of those sides closing up with each of those interior angles at 157.5. Next example, the measure of each angle in a regular polygon is 162. How many sides does the polygon have? So I'm looking at this first part right here. The measure of each angle in a regular polygon. That was the formula, n minus 2 times 180 divided by n. This is the formula for the measure of each angle in a regular polygon. This is equals 162. The goal here is to solve for n. So doing some algebra, I don't want n in the denominator, so we're going to multiply both sides by n. Distribute over on the left, so 180n minus 360 is equal to 162n. How about we subtract 162n from both sides, add 360 to both sides, and now divide both sides by 18, and we get n equals 20. If you have a 20-sided regular polygon, each of the interior angles then would be 162 degrees. So consider 20 sides. The other thing we have for these regular polygons is the exterior angles. And if it is regular, again, we're going to have something that's very specific for us. So start at the very beginning. In a triangle, the sum of the interior angles is 180 degrees. And if it is regular, it doesn't have to be regular, but we're going to focus on the regular one right now. I want to look at an exterior angle from each vertex. If it was regular, we'd have 60, 60, 60. I'd make this 120, 120, and 120. So each of those exterior angles would be 120 degrees. 120 times 3 gives us 360 degrees. Again, I'm focusing on the regular. If this changed by a little bit, let's say instead of it being exactly regular, let's say it was 60 and maybe 90 and 30, they still add up to 180 degrees. This would be 90, this would be 150. And if we still added all of those together, 150 plus 90 plus 120, it still would come out to 360 degrees. Right, quadrilateral. The sum of the interior angles is 360. If it's irregular, 360 divided by 4 means that each interior angle is 90. So I'll just go ahead and draw this. So 1, 2, 3, and erase a little bit of this. We only want one exterior angle. So here's our fourth one, 90, 90, 90, 90. Each exterior angle is 90. 90 times the 4 once again gives us 360 degrees. Again, I'm focusing on the regular, although it could be any convex polygon, and this is would still work for us. Things would just slide around a little bit. We'll do a couple more here. Pentagon, the sum of the interior angles, I found it before. I just know it's still 540 degrees. 540 divided by 5 means that each interior angle is 108. Regular, each exterior angle is 72. 72 times 5, again, the pentagon would have 5 exterior angles, would give us, once again, 360 degrees. Hopefully you're noticing the pattern here. Hexagon has 720 degrees. 720 divided by 6 means that each interior angle in a regular hexagon is 120. take 180 minus that because an interior angle and an exterior angle are supplements. They form a linear pair. So the exterior angles would be 60. 60 times 6, believe it or not, is 360 degrees again. So we can keep going and going. I'm going to say, let's go down to an n-gon. So it's a polygon with n sides. The sum of the interior angles is that formula, n minus 2 times 180. Each interior angle is also a formula for us, n minus 2 times 180 divided by n. So then each exterior angle would be 180 minus that, which is looking like a pretty complicated formula. And then the sum of the exterior angles, we always multiplied n by whatever this column was. Or as you see, the pattern is it's always going to be 360 degrees. What that tells me then, if I go back to this column, I could take 360 divided by n, the number of sides, 360 divided by 6, 360 divided by 5, and so forth, to figure out how big each exterior angle is. So in other words, if the sum of the exterior angles is 360 degrees, and it has n sides, we could also say this is 360 over n for this column. If we did the algebra and simplify this, it actually would come out to 360 over n. But that's how we can figure out the measurement of each exterior angle as long as the shape is regular. Again, for these two on the inside, this is assuming that the shape is regular, whereas these two outer columns, some of the exterior and some of the interior, is as long as it's convex. It doesn't have to be regular. So in conclusion here, if you have a convex polygon, the sum of the interior angles is n minus 2 times 180. The regular polygon, we could say that each interior angle is n minus 2 times 180 over n. And as far as the exterior angles go, the sum of the exterior angles is always going to be 360 degrees. And if it's regular, there's a stipulation on there, if it's regular, then each exterior angle would be 360 over n. So these are the two primary formulas we're looking at for interior. And for exterior, as long as it's convex, the sum is 360, and each exterior angle is 360 over n if it is regular. And then we'll finish off with a couple of questions here. First one is a convex pentagon. It might be regular, I don't know, but it's definitely convex. So we're going to add up all these angles together. So add up all the terms, 5x plus 4x plus 6x plus 7x plus 4x. Let's see, it's 9, 15, 22, 26x. Add up all the numbers, that's 0, 10 plus 20 is equal to 540 degrees. Where did I get 540? Well, in a convex pentagon, the sum of the interior angles is 540. I was using that formula, 5 minus 2 times 180. So then subtract 20 from both sides. Divide both sides by 26, and we get x equals 20. Last example, we have this convex quadrilateral. We have 3 of the interior angles and 1 exterior angle. If I add up all the interior angles, I know it's 360 degrees. The problem is this is an exterior angle. I want the interior angle. Now, the relationship between these two angles is that they're a linear pair. They're supplements that add up to 180 degrees. So if I subtract 180 minus that, there's our interior angle. So now when we add up all 4 of those interior angles together, combine the x's, negative x plus 2x, plus add all the numbers, 180 minus 10 is 170, minus 170 is 0, plus 90, that's equal to 360 degrees. Subtract 90 from both sides. Now divide both sides by 2, and we got x equals 135. Now, does that make sense? If we plug 135 in here, that'd make this angle 45. 135 minus 10 is 125, and then 2 times 135 is 270. 270 minus 170 is 100. Great. All those angles work with this angle being 90 degrees, so x equals 135.